Hello everyone, welcome to the sixth video in the linear algebra series. In this video I will talk about eigenvalues and eigenvectors. So first we will define what both of these words mean. So let A be a square matrix. A scalar lambda in our field F is called an eigenvalue of A if there exists a non-zero n-vector x such that this equation holds. So Ax is equal to lambda x. This vector x, we call it an eigenvector of A corresponding to lambda, where lambda is, again, this eigenvalue. Additionally, we have another definition, which is called the spectrum of a matrix A. This is the set of all its eigenvalues. So the set of all lambdas which satisfy this definition. So there exists a non-zero n-vector x such that Ax equals lambda x. And basically the idea behind an eigenvector is that a matrix acts on its eigenvector like a scalar. So the way we see this is that we go from Ax to lambda x, where lambda is a scalar. So multiplying by A is like multiplying x by a scalar, which is lambda. And an important thing to note is that this x is non-zero. Have I said that here? Yes, non-zero vector x, because if we could allow a zero vector, then it would be an eigenvector of any matrix, and any scalar would be an eigenvalue, because multiplying the zero vector by something does not change the fact that Ax equals 0. So this is why we exclude the zero vector. So now that we know what an eigenvalue is, we want to know how to find them. So we can view this equation, Ax equals lambda x, as a system of equations with unknowns lambda and x, because of course we do not know the eigenvectors and eigenvalues yet. We can rewrite it in this way, so we just bring this term to this side, and then we get a minus lambda I. We have to add this I here, because if we take out this x, we cannot just leave the lambda, because a minus lambda does not mean anything, because A is a matrix and lambda is a scalar, we cannot subtract them. So we get this expression, a minus lambda I x equals 0. From this we see that lambda is in the spectrum of A, so lambda is an eigenvalue of A if and only if there exists a non-zero x, so a non-zero vector, that satisfies this equation. So equivalently, if this linear system has a non-trivial solution, what we can remember from before is that if a matrix is non-singular, then this linear system has only a trivial solution. So clearly this is equivalent to this matrix being singular. Yeah, so which is equivalent to having a zero determinant. From this we can conclude the following. So we have that lambda is in the spectrum of A, so lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is 0. So let's go over this again. So lambda is an eigenvalue of A if and only if there exists a non-zero x satisfying this, which is the same as this having a non-trivial solution, which is the same as this being singular, which is the same as it having a zero determinant. So there's a long chain of equivalent conditions here that we've derived in the videos before. So with that, we can find the eigenvalues just by setting the determinant of A minus lambda I to 0 and solving for lambda. So to do this, we first need some other results which describe the determinant of matrices of the form A minus lambda I. So let A be a square matrix, then this determinant is this very nice polynomial in lambda with these coefficients, and we have that it is a monic polynomial. So the first term is always 1, always is coefficient 1, sorry. And this motivates this definition. So the polynomial P sub A, which is the determinant of A minus lambda I, we call it the characteristic polynomial of the matrix A. And as I mentioned before, we want to set this equal to 0. So this thing is equal to 0. And every lambda that satisfies this condition will also satisfy this condition. So lambda is in the spectrum of A, so it is an eigenvalue of A. So we see that the roots of the characteristic polynomial of a matrix correspond to its eigenvalues. By the fundamental theorem of algebra, which is beyond the scope of this lecture, we have that a polynomial of degree n has n complex roots. So an n by n matrix always has n eigenvalues because its characteristic polynomial has degree n. So there will be n values of lambda that satisfy this equation. If you do this, then there will be n values of lambda, n not necessarily distinct values of lambda that satisfy this equation. Okay, so let's look at an example. So we have this matrix, and we compute its characteristic polynomial. So that is this expression here, just by setting the determinant, computing the determinant of this. So again, the way we do that is we, why is there a 1? Okay, anyway, we multiply this by this and subtract it by this, so we get, it's a typo, it's supposed to be a minus. I'll fix that. Okay, so then we get this squared plus 4. And yeah, if we expand this, we obtain this expression, and then using the quadratic formula, we can obtain these roots. So these are our eigenvalues. And now to find the eigenvectors, we want to solve this system. So we want to find the x that satisfy this. And now we know lambda, so we can just plug in our values of lambda, which we do here. And then we can solve for x1 and x2. And if we do this through a row reduction, we find that this is an eigenvector, and where this alpha can be any scalar, because we have a free variable here in the form of x2, as you can see. Similarly, we can solve for the second eigenvalue and find a different eigenvector also with this scalar alpha that we can pick as we please, as long as it is non-zero, of course, because we cannot have a zero eigenvector. Now we have some very nice results that relate sums and products of eigenvalues and determinants. And first we define the trace of a matrix. So the trace of a matrix is denoted by TRA, we just call it the trace of A, and it is the sum of all of the diagonal entries of A. Then we have this result. So the trace of A is the sum of all its eigenvalues, and the determinant of A is the product of all its eigenvalues. A nice corollary of this last result is that if a matrix has a zero eigenvalue, then its determinant is 0, because if any of the lambda in the spectrum of A are 0, this product will be 0, so then the determinant of A is 0. Okay, that concludes the video on eigenvalues and eigenvectors. I hope you enjoyed it, and I will see you in the next video on diagonalizability.